So as has been mentioned before, when we were doing maximum and minimums, the optimization problems are one of the primary applications of calculus to real-world problems. So in the regular class, we'll talk extensively with a bunch of different applications of optimization, but for this flipped class video, we're going to focus on just one particular example coming from economics. So let's go ahead and review some definitions here to start with. So the cost function, C of Q, is just the cost to produce a quantity of Q products. So if you're going to produce 10 products, C of 10 gives you the cost to produce those 10 products. The revenue function, R of Q, this is the total revenue received from selling Q products. So generally the revenue function here is defined by P times Q, where P is the price of the product and Q is the number of products sold. Obviously, the price of the product will depend upon several things, so that will usually be a function of Q as well. And finally, the profit function, what we're usually interested in, is P of Q, which is the revenue, so how much money we bring in, minus the cost it made to produce those items. Usually, we're trying to maximize the profit function. So what we're often interested in economics is the marginal cost. So what's happening at the margin? So you know you're making a certain amount of some product, and then you want to ask, well, should I make more of the product or not? So basically, you know, if you produce more of the product, the cost is going to go up, but you're also going to bring in more revenue if you sell more of the products. So what you're trying to do is you're trying to figure out, well, which of those is going to be larger? You'd like the revenue to be larger than the cost if you're going to increase the number of products. And then you'd like to basically figure out, given this revenue and the cost functions that give you the profit function, you'd like to figure out how do we maximize that profit function. So the additional cost to produce one more product is from C of Q to, or from Q products to Q plus 1 products is just C of Q plus 1 minus C of Q. But economists generally define the marginal cost to be C prime of Q. So just take the derivative of the cost function. And one reason this is useful is we remember that C prime of Q, that would be the slope of the tangent line to the function C of Q at Q. And this is approximately the slope of a secant line, which would be CQ plus 1 minus C of Q over Q plus 1 minus Q, which is exactly CQ plus 1 minus CQ. So we can approximate this difference here by the derivative. Similarly, we can define the marginal revenue. So the additional revenue to produce one more product additional revenue to produce one more product would be R of Q plus 1 minus R of Q. We define the marginal revenue to be R prime of Q. And note that R prime of Q, just like before, is approximately R of Q plus 1 minus R of Q over Q plus 1 minus Q, which is R of Q plus 1 minus R of Q. So now we can use these definitions to look at how are we going to try to maximize our profit. So this means what we're trying to do is if we're given this profit function P of Q on some interval A less than or equal to Q less than or equal to B, so A is the minimum amount of product we can produce and B is the maximum amount of product we can produce. We want to maximize this function on a closed interval here. So what we want to do is we want to find critical numbers on the open interval from A to B and then evaluate the endpoints as well. So we're trying to find the absolute maximum of P of Q on the interval. So one thing to note here is remember that P of Q is R of Q minus C of Q. So P prime of Q is R prime minus C prime. So that means when the derivative of the profit is equal to 0, that's when the marginal cost is equal to the marginal revenue. And that will give us our critical numbers inside the open interval. So let's go ahead and just run through one quick example of how this shows up. So let's suppose we have some revenue function here, R of Q, given by 5 times Q minus 0.003 Q squared, and C of Q is 300 plus 1.1 Q. So in our interval to look at is we could produce 0 products or we could produce up to 800 products. Another thing to note here is that note that C of 0 is 300. So that 300 is our fixed cost to get things started. We're going to have to spend that 300 even if we produce no products. So if we look then of R of Q minus C of Q, we get that 5Q minus 1.1Q giving us 3.9Q. And then we have the minus 0.003Q squared minus 300. And that's our profit function. And so now we want to find the absolute maximum value of P of Q on this closed interval from 0 to 800. So we take the derivative of P and we get 3.9 minus 0.006Q. So we see the critical numbers of this are when P prime of Q is equal to 0, and that happens, solve that equation, 3.9 minus 0.006Q equals 0, and that comes out to give us 650 for Q. We can check, even though we're working on a closed interval, so theoretically, so strictly speaking, we don't need to do this step, but we can see that P double prime of Q is minus 0.006, so this Q of 650 does give us a local maximum. And now we can just evaluate the endpoint. So we see P of 0 is minus 300. Remember, that was the cost for us to just set things up, even if we produce 0 products. P of 650 is $967.50, and P of 800 is $900. So that tells us producing 650 of our product is going to give us our maximum possible profit. Producing 0 of them would give us our minimum, absolute minimum possible profit, where we would have a loss of $300. And so that's how we can apply optimization to look at a problem in economics.